Hello and welcome. My name is Alencar Xavier, and I'm here presenting today leveraging correlated information under multivariate settings. That is a presentation regarding the paper that I wrote with my colleague David Javier. A new approach fits multivariate genomic prediction models efficiently. Well, that's a brief outline of the presentation I'll be giving today. I'll start with a high-level rationale and start moving towards the statistical model that represents the problem we are trying to tackle. We are going to cover how we would be estimating coefficients and then how would be estimate the variance components. Coefficients and variances are the two main things we try to estimate when we are trying to fit a multivariate model. Later, we are going to move into the simulations where we are going to present how our model compares to standard operations models, including RAML, for instance. All right, so let's get started and jump straight into the rational and statistical model. So, as you can imagine, many of us have the background in plant breeding, and one of the main objectives of a breeder is to improve the realized yield in the farmer's field. So in the analogy of the law of the minimum, when you have a barrel, the water will represent this yield that farmers realize in their farms. Of course, the amount of water in the barrel is always limited by the most limiting factor. Usually we think that those factors may include the potential, a resistance to a given stress, the stability of the material, diseases, and pest resistance. And as we identify these problems in our germplasm or in the lines, we try to address them through breeding such that we might be able to increase the yield farmers get. Well, we do operate upon multiple traits at the same time. And we are also aware that single trait models for genomic prediction in plant breeding are already well established. Some of those you might know as GBLUP or base B models, where you have one phenotype, series of genotypes, and you calibrate this model connecting genotypes and phenotypes. However, phenotypes may and do come from multiple locations, years, and quantitative traits. Many of those are genetically correlated, and one may consider using the genetic correlation among those traits to enhance the prediction, thus adding more information to every single prediction. So the rationale behind working with multiple correlated traits can be depicted here in a couple aspects. Well, we know that we can capture complex genotype by environment patterns if we decided to model the multiple environments as different traits, where they are considered correlated traits but not necessarily the same. So we can also do the same if we perform this modeling with multiple phenotypes. And that usually translates in higher accuracy, because if you are jointly model correlated traits, you'll get extra power and more accurate estimators of breeding values. Second, we can assess phenotypic traits. We know that we are working in the era of phenomics. We generate data from multiple phenotypes, and the applicability of those phenotypes is measured by the genetic correlation between these high throughput traits and traits of interest, which could be things like yield, moisture, maturity, plant height, and disease scores. However, it's very nice to know that even though multiple trait models, multivariate models, multi-location models can be very beneficial from the theoretical standpoint, we also know those are computationally prohibitive. Why? Because every one trait you add into the model, you can increase the computational cost by the number of traits in the exponential 7, according to Zoe Steffens 2014. So modeling multiple traits is not a common practice in the sense that it has not been a feasible technique to deploy. That being said, if multivariate models become more and more efficient over time, we know that there are plenty of applications that go beyond the genomic prediction per se. So here I'm providing two examples of what we can do with those genetic correlations, the multi-trait heritability values, and on the left I'm depicting two approaches of reduction of dimensionality that showcase and inform the trade-off among traits. So that's from a study that I did in soybeans a couple years ago. We have a principal component that is basically the eigendecomposition of the variance-covariance matrix of the genetic correlations. Well, more precisely the genetic correlations. So one thing that we see here, yield and reproductive length are aligned to the same vector. And on the right, what I have here is a graphical model also built upon the genetic correlation among traits, showing that yield is directly connected to three other traits, ACC, which corresponds to average canopy coverage, the number of nodes in the soybean plant, and the length of the reproductive period, here depicted by the abbreviation REP. So those are just a depiction of what you can do learning the trade-offs when you are feeding multiple traits. On the right, on another hand, we are doing a environmental classification where we treated different geographies as different traits. I ran the multivariate model, and I was able to create this map based on the genetic correlation among locations, which puts into perspective which locations have a better alignment in genetic terms when I'm breeding for different regions, and data from where could be leveraged where else. That can be also informative to determine or districting your target population of environments. That means that I can distribute my field trials differently, reallocate my resource differently, based on my knowledge of this environmental classification that was purely based on genetic performance and how the genetic performance and ranking align from the different regions. I do not require for this analysis that all individuals be planted and observed in all locations. That's one of the beauties of multivariate models. They are connected through genetics, not necessarily through phenotypic records. So why would multivariate models be any better than the models we currently run by modeling one trait at a time? So here you can imagine that any phenotype described by the vector y could be a function of the genetics plus environment or genetic plus residuals. And the gain of information when this y is multiple traits is basically the correlation between trait 1 and trait 2. The variance of this joint vector y1 and y2 is depicted here, that the correlation we observe on the phenotype could be coming either from the genetic component, here depicted by the covariance A12, or by the residual covariance, here the sigma E12. So basically we are objectively adding more information into the model. Well, that looks a little high level, but I will show you in this slide here that we can actually compute where this gain is coming from. So from the same model, shown in the previous slide. Now I'm using matrix notation to showcase the same gain of information we would have using genomic information to estimate breeding values in a univariate model here below represented by G1. And on the very last line, what I depicted is conditional to the secondary trait, how we would be computing G1. And what I highlighted in yellow in this slide is objectively the information gain we get by modeling G1 conditional to G2. So even though it seems to be a straightforward solution, the fact that we are simply adding more traits, there's a whole chunk of the equation that is added when we are conditioning traits or fitting them jointly. Alright, so next, if you care to read the study we published, you see that we try to focus not on the GBLUP based on relationship, but instead using ridge regression, which is an equivalent framework. So regression type models are nice because if you store the marker effects, the beta coefficients, you can very nicely use them for predicting new data sets, as opposed to GBLUP, where you have to carry the estimation set with you every time that you want to predict newer individuals. Besides, ridge regression is easily compatible to multi-stage framework, where we use blues to adjust for the spatial variation. We take those blues, we connect into multi-environment BLUPs or deregressed BLUPs, and we use those to fit linear models that include genomic information, which is a more computationally efficient way to handling the data. The third point here that I want to make is that ridge regression is a Gaussian model. It's fully additive depending on how you parameterize, but generally additive, and it is equivalent to GBLUP, and that's a known property of it. A big advantage of dealing with ridge regression as opposed to GBLUP is that we don't have to create or invert the G matrix. And that's an advantage. Why? Because G is not always inversible, and every time that you have to do some sort of bending or adding a value to the diagonal of G, you actually are choosing to lose precision. So the G matrix can be cumbersome, especially because we work in planes where more often than not we have more observations than markers. And last but not least, regardless of whether you use ridge regression or GBLUP, when you feed those models under the multivariate framework, you get this nice covariance and variance components that provide statistics that are very meaningful for breeders. That would include heritability, reliability, accuracy, genetic relations. From those you can create selection indices, and with the covariance components you can also calculate the correlated response to selection. Alright, so how does this ridge regression model works in the multivariate framework? So the model looks pretty much like a univariate model would look like. You have your response vector of y, which corresponds to the phenotypes. We have the mu, which is the overall mean or intercept. Beta here corresponds to the marker effects. The vector E corresponds to the residuals. And the matrix Z is a block diagonal, where the diagonals have the genotypic matrices from the individuals from the various traits. Recall that you may or may not have any overlap of individuals between the different locations or the different traits. So why is that multivariate in any sense of the word? Well, because the covariance of beta, the marker effects. It's distributed as such that every time you update the marker effect for any given trait, it actually follows this covariance capital sigma beta that connects all the traits together. For this specific model we will be working today, we are going to assume that the residuals are independent, meaning that each trait will have its own residual variance. However, the residuals between traits will be independent, and that's a very valid assumption, because if you imagine that you're modeling individuals from various environments, there's no reason to believe that the residuals would be correlated by any reason. So you can imagine that if we follow in the traditional multivariate framework this model we just described, the mixed model equation depicted in this slide can be enormous. And that's because every time we try to fit a model that is jointly modeling multiple traits, we have to operate using Kronecker products. That implies that the dimensions of the left and right side of our system of equations becomes really big. And another thing to keep in mind is that every time we compute or update the variance components, we have to invert the left-hand side of the equation. So just to illustrate, if we are working with maybe 3 traits and you have 1,000 markers, when we are working with univariate framework, the left-hand side would be 3 times 1,000 by 1,000. However, working with multivariate, you're going to have one 3,000 by 3,000 matrix. So I can safely say that as the number of observations and marker increase, fitting multivariate models, at least under the general sense or how it's usually done in the current framework, it's impossible. And here I want to just create the sense that it's a problem we're trying to address, we have been thinking over, and really computation is a resource that is still as expensive, even if we go through cloud computing. Modeling such large models may or may not converge, and it may take a large amount of resources. That will be time, that will be the cost of the computation, and you can imagine that we really need to get those values as soon as possible to make the breeding decisions. So here I just put it as unless, because drum rolls, we are going to really try to capitalize and focus on how to address this computational limitation in this presentation. All right, so let's move on to the coefficients. You may or may not know that every time we are feeding a model in that say apply to genomic prediction, we have more often than not more parameters than observations. So you can imagine that many models like the ridge regression blob, Bayes A, Bayes B, and all those Bayesian methods, we will be feeding a large number of markers, and more often than not more markers than observations. So it's a hyperdimensional model. The way how that is done is through a methodology called Gauss-Seidel. Why do we do that? Because handling such a large number of parameters does not justify creating the system of equations. So the first thing that I want you guys to keep in mind, we will be using Gauss-Seidel, which means that we will not be setting the mixed model equation as you probably have learned in quantitative genetics or the basic genetics class. So that's very nice, because we don't have to do that x prime x, z prime z. Instead, the way how Gauss-Seidel works is by feeding one marker at a time, getting the residuals, and feeding the next marker. So here I'm depicting by a illustration where you can clearly see that the way how the model is updated is by feeding one or a few markers at a time, and you do that over and over and over, and the model eventually will converge to the exact same solution as it would if you were setting the system of equations. How would that look like in the multivariate setup? Well, the formulation is rather similar, except that when we update a marker, we update that marker effect not as a single value, but as a vector, because the marker effects associated to the multiple traits now, you can imagine that instead of fitting that one marker for one trait, you're fitting that marker for several traits. So if you have 5 traits, beta will not be a single value, but instead a small vector of length 5. So that means that we will be running the Gauss-Seidel in a small system of equations 5 by 5. It is yet possible to notice that even though we are now fitting this small system of equations that has the same dimensions of the number of traits, we can go a step further and use conditional expectations and fit one by one using vectorial mathematics. But the whole idea that I want to really convey here is that the formulation we use in the multivariate system of equations using Gauss-Seidel is really small. Instead of fitting those huge markers involving large Kronecker products, instead, by fitting one marker at a time, we are handling very small matrices that for the simple example here is just number of traits by the number of traits. So the idea is still as fit one marker at a time, take the residuals, feed the next marker. And the nicest thing, we are avoiding that big Kronecker product altogether, and we are not doing any matrix inversion, and still we are getting all the advantages of a multivariate model. So one of the only matrix that we actually have to invert, and that's only once every full iteration cycle, is the variance covariance matrix of marker effects, here depicted by capital sigma beta. So that here I'm just further depicting how that loop would look like. So basically I'm color coding on what do we compute once, what do we compute once every iteration, and what do we compute in each marker within each iteration. So in green are things that we compute before even starting the loop. So the zeta prime zeta for each trait is computed only once before the loop even starts. In orange are the marker effects and zeta prime error, which we do compute for every marker within each iteration. And in blue here are the variance components, which we compute once every iteration, but not for every marker. So we just computed once in each iteration. And if you recall, one of my first slides where the covariance was the information being added into the system of equations, that is where most of the benefits come from. So here in this bivariate example, we can clearly see that the sigma beta occupies those off diagonals that correspond to the covariance between traits. Another thing that we point out in our study is a rather new discovery that corresponds to the fact that if you update the markers in random order, you can truly speed up the convergence. So on the left here, we are updating the marker effects in random order using the randomized Gauss-Seidel, and the whole mixed model equation with 10 traits and 5,000 observations and 4,000 markers converged within 50 iterations, probably a 20-30 seconds operation. The same model with the same data if we update the marker effects using ordered Gauss cycle, meaning a loop in the same sequence of markers, it took as many as 3,000 iterations. Well, to be fair, 3,000 is still much less than what you'd have to do if you were to do Monte Carlo. If you were to fit your model using MCMC, which is between 30 and 100,000 iterations. But you can reduce dramatically this number of iterations from 3,000 to 50 just by updating the markers or marker effects in random order. In fact, the randomized Gauss cycle is something that came from the machine learning literature as opposed to the classical quantitative genetics statistics literature. Alright, so now that we know how to update the marker effects, you may be wondering, where do we get those variance components from, right? So I'll briefly show how that's where we're getting those variance components in the univariate and the multivariate case. First, a very brief history of variance components. The whole variance terminology came from Fisher in 1915, but prior to that there were analyses that were not yet named ANOVA, but they depicted the same principles of that type of analogy. So in the very top, I'm mentioning this reference of Airy, 1861. The theory of ANOVA is formalized in 1921. Keep in mind, ANOVA is a nice framework, but it has some very strong assumptions. It requires balanced data, and it can hardly handle complex covariance structures. 1953, Henderson published a manuscript where he generalized ANOVA to an infinite number of fixed and random effects. So one of the breakthroughs was starting introducing matrix notation within the variance components literature, which has been a limiting factor. So that was 1953. 1962, the idea of a restricted likelihood is becoming more and more mature, and the term RAML was proposed. From that point, you can imagine that computation was a very limiting factor, and there were two possible paths to which Henderson methods and restricted likelihood methods would pursue. So on the right here, I'm depicting the exact likelihood path, which started with that idea of estimating the maximum likelihood function, which could be maximized. At a time was proposed to start using things like the expectation maximization algorithm in case there was no exact solution. And at a lighter computational cost on the left, I'm illustrating methods that were iterative at a time. So some of the first iterative methods that became quite popular were proposed by Cunningham and Henderson in 1968. The same method was later corrected and generalized by Robin Thompson, to accommodate non-orthogonal design matrices. Henderson kept working in iterative methods. So one of the methods that became also quite popular was called the Henderson simple method from 1980, and some iterative variations that he proposed with his student Van Vliet. Going back to the RAML path, as this idea of likelihood and quadratic expectations evolved, there was part of the literature that branched out to MIFQ and MinQ frameworks. Those were largely the contributions of Rao. Very nice framework, but with a very dense matrix notation. At the same time, Patterson and Thompson, they were working towards providing more and more insights, making RAML a more clear approach to pursue. So in later years, the methodologies by which we estimate variance components in our plant and animal models was established by Henderson, and it had plenty of iterations and intermediate solutions. Some of the solutions that became really famous were through derivation-free RAML, where we use numerical methods and assess the likelihood. And one of the most modern implementations of RAML is the average information from Johnson and Thompson from 1994, which is implemented in software such as ASRAML, BLUPF90, and others. However, there was this one branch that I left for last that I call the fast variations. So we know that RAML became the gold standard, but there were also fast variations that were not necessarily RAML, but they were unbiased, they were inexpensive to compute, and they have similar properties as RAML, though they don't share all the exact same properties. They were, invariant, center invariant, unbiased, but for a reason or another, people did not pursue any further. So two of those methods were the pseudo expectation proposed by Schaeffer in 1986 and the tilde hat method proposed by Van Reyden and Jung in 1987. This one, the tilde hat, is more often than not referred to as a Van Reyden method. So the nice thing about those methods is that at a time, the authors, both Larry Schaeffer and Paul Van Reyden, were analyzing data sets with millions of individuals in late 80s, so they have plenty of data. They were using the animal model to calculate BLUPs of breeding values and really working in the theory of animal breeding. However, they didn't have the computational power to estimate the exact RAML solution, so they proposed these creative ways of calculating variance components. And once again, many of those methods were created to handle very large data sets, and for a reason or another, they were forgotten as we move into the genomic era. So here I'm just briefly describing how it came to be these variance component methods. So on the very top we have the first derivative of RAML, we have that restricted likelihood, and then we do the first derivative with respect to the sigma squared beta. And on the top we have the covariance between y and u, which is ypv py. Here are all the definitions of the P matrix, which is the null space projection, divided by the trace of PV. Oh, very nice. You could get the RAML solutions through this derivation, but that would entail that you need this V inverse matrix and matrices such as the covariance of K. So in 1986, Schaeffer proposed this method where he said, well, maybe if we get rid of V altogether, we can come out with a very simple expectation where, keep in mind, whenever you see traces, we don't actually compute the trace. We don't have to build the z prime z, we just compute directly the diagonal elements. So we never get to do the z prime z. So that was very nice because this type of framework is directly compatible to the things we have to generate to solve the Gauss-Seidel. And then a year later, Van Reyden proposed that maybe we can do a slightly better job, not by getting rid of the V inverse matrix, but by replacing by the inverse of the diagonal elements, which is much simpler to compute and yet can preserve some better statistical properties and keep it closer to the RAML solution. Besides, if your model is close to orthogonal or unstructured, the tilde hat will likely give you exactly the same solution as RAML. The name of the method is called the tilde hat because he approximates one side of the equation by calling the yd minus 1z as b tilde. So both methods are equivalent as long as if the D matrix is just an identity matrix, the tilde hat is reduced to the Schaeffer method, pseudo expectation. So why do we care only about the genetic covariance? Well, because the residual covariance under RAML or any other method is really straightforward to be computed. So the really hard variance component to get is the genetic variance covariance. Plus, not having to do V, we are, it's a very painful matrix to compute. It takes a lot of memory, so we do not want that. And notice that here we are not using anything with the C matrix, which is the left-hand side of the mixed model equation either. So basically, what do we keep in memory, or what's the solution of those variance components? It's rather straightforward. It's just the b tilde times the prime b hat divided by the trace. One more time, we don't have to calculate z prime z in the inverse. We just use the diagonal elements to get the trace. Same with the covariance. It's just the tilde hat from trait 1 and 2 plus the hat and tilde of traits 1 and 2. We get the same solution as Schaeffer by just assuming that D is an identity matrix. We have very few things stored into memory, just the B hat, the B tilde, and some of the diagonals of ZPZ. The beauty of these algorithms is that we do not have to keep in memory the variance covariance matrix. We don't have to keep in memory the left-hand side equation of the Anderson. We don't have to calculate determinants, and we don't have to do any dense inversions at all. A more intuitive derivation of the Schaeffer method, it would be simply getting the corrected values or centered values of trait A being predicted by B, and the B being times the prediction of B from A. So a intuitive interpretation of genetic covariances would be how well A predicts B plus B predicts A, and you take somehow like an average of it. So it's a very intuitive derivation being projected in mathematical terms. What do we do with all these variance components? Again, it's very nice. We can get the genetic variance, we can get heritability, and we can get genetic correlation among traits. So those are all very informative genetic parameters, very applicable to plant breeding, and you can solve all of those very efficiently. So the model not only gives you the marker effects, but gives you the components you need to calculate heritability, variance components, and genetic correlations. So let's go now to the factual benefits and the comparison between the proposed method and the gold standard. The metrics we have been evaluating for this study include the computational efficiency, which is basically how long it takes to fit the model. When evaluating the breeding values, we're going to check the accuracy, where that is defined by the correlation between GBVs and true breeding values. And last but not least, we want to look at bias and precision of our coefficients, where bias is the expectation of the difference between our estimator and the true value, and the precision corresponds to the standard error or standard deviation of this measurement. We're going to look into two scenarios from two data sets that are publicly available. One is a wheat data set available in the BGLR package, and the other one is a soybean data set available in the SoyNum package in R. The first scenario, we're going to use the genomic available in the true data set and simulate phenotypes coming from 10 environments where all individuals have been observed in all environments. However, so we are calling this small data set the balanced data set because everyone has been observed everywhere. The second one is called the unbalanced scenario, because we are using the true genomic data but simulating phenotypes from 10 environments. Each individual will be observed in a single environment, and the number of lines per environment is 514. So we just observe 10% of the data set in each environment, and we're going to fit the 10 environments being treated as 10 different traits. And the number of markers is slightly different. In one case we have 1200, and in the soy data set 4300. One thing that I have to disclose is that under the unbalanced scenario in the soybean data set, we were not able to get RAMO genetic covariances. Whenever we had zero overlap of records, the estimated values from RAMO are all anchored at zero. We tried that in ASRAMO, RAMO F90, AI-RAMO F90, and a couple other software, and in no implementation we were able to get meaningful variance-covariance components from RAMO. Once RAMO has some overlap of individuals, the estimates of variance components became available, but in that soybean data set we were not able to get any, so we will not be, unfortunately, benchmarking against RAMO in one of our scenarios, simply because RAMO could not be used in such an unbalanced scenario. Alright, so let's look at the how long it took to fit the model into the small data set that was balanced. Here we use a couple of different softwares. The methods we proposed, we named them PEGS and THGS, meaning pseudo expectation Gauss-Seidel and tilde hat Gauss-Seidel. The software we compared against were ASRAMO 4.2, that took 272 seconds, AI-RAMO F90 took 100 seconds, and the Gibbs F90 took 560 seconds. The proposed methods that we discussed in this presentation took less than a second, so 0.27 for the multivariate case, and we also fit the univariate tilde hat Gauss-Seidel one trait at a time, and we added them up, and that added up to 0.23 seconds. For the second scenario, where we do not, unfortunately, have RAMO, both PEGS and THGS gave roughly the same elapsed time, so we don't have to compare one against the other. But what we can do is to increase the number of traits to see how long that will take. To fit the model. So on the left we are checking what would happen if we were to fit that model with 4,000 markers or 42,000 markers, where the number of traits is 10, 50, or 200. And here's the elapsed time. So to fit 10 traits, it took 0.2 minutes, so less than a minute. To 50 traits, it took us 3 minutes. And notice that even if the number of markers is really high, 10 traits is still under a minute, 50 traits, roughly 10 minutes. And then with 200 traits, it took 80 minutes, so a little over an hour. And with 200 traits and a large number of markers, it took 2 hours. Still, that number of traits and markers would be rather inconceivable to run with a RAMO solver. Now let's look at the accuracy. So, because our phenotypic records are simulated, we did have the true breeding value, and we could directly assess what's the impact in accuracy by using RAMO or the different methods. So on the left, we are also trying here the TVGS, which is the true value of various components fitted with Gauss-Seidel. So that was always the very best because we were using the true variance components. Variance components estimated through RAMO were equivalent to the tilde hat and pseudo expectation. So the accuracy with our proposed methods really captured the same covariance among traits that you'd get from RAML, so that's fantastic. And what you can see is that the univariate methods falls behind because it cannot leverage that information across traits. The general trend is that high genetic correlation and low heritability favors multivariate methods over univariate methods, but besides that, all multivariate methods provided very similar accuracies. Of course, using the true values for the variance covariance was the very best. Then RAML, THGS, and PEGS. Now let's look at the bias of the heritability. So the largest discrepancy we saw in the comparing RAML to the proposed methods was 0.05. That happened when the heritability was really high and the genetic correlations were low. So the proposed methods, they underestimated the heritability of the trait by on average 0.05. Now the bias of the genetic correlations. At full disclosure, genetic correlations are things that are really hard to estimate in general. It's hard for RAML and it's hard for all the methods. A very interesting thing here is that when we had high correlation and low heritability, the difference is 0.07, not because our method was bad, but because RAML was unable to do a good job. So under those circumstances, RAML, not our method, underestimated the genetic correlations by 0.08. And then in the next scenario, RAML overestimated when the heritability was 0.5 in high correlations. RAML overestimated the correlation among traits by 0.07. So another thing to notice, the soybean data set is larger in the sense that it has more individuals and more markers, and the heritability and genetic correlations are largely unbiased. Now precision. So precision is the standard error of those heritability and genetic correlations. So let's start with the precision of the heritability. So it's true the pseudo expectation and tilde hat had a standard error larger than as the ones of RAML. So something had to give, and one thing that our methods is a little worse than RAML is the precision of the heritability and genetic correlations. Similar trend here now depicted in the genetic correlation is that our methods, especially when the correlation among traits was low, it had a larger standard error than RAML. Here, on average, 0.07 larger. But fear not, our method was actually meant to be used in larger data sets where it's not possible to fit RAML. So as the amount of data increases, you get less bias and more precision. So here we ran a quick comparison using PEGS, THGS, in the univariate THGS with either 250 observations per environment or 3,000. So in the soybean data set, we had as many as 5,000 individuals, so it was fine to use up to 3,000. It was not even half of the data set. So the accuracy has a tremendous improvement as you increase the number of observations. That is true for univariate and multivariate settings, more so for the multivariate. The slope or the bias of breeding values, as we got to the 3,000 observations point mark, it went from slightly biased downwards, 0.98 to 1, so it became fully unbiased. The bias of heritability was very small, 0.01, not significantly different than 0, and even 0 in the THGS case. But overall, I would say that slightly underestimated, but not different than 0. The standard error of the heritability dropped from that 0.07 we were looking at earlier to 0.04, and presumably, which was the same as the RAML report. But presumably, as the number of observations increase, your standard error, your precision will increase, standard error will decrease. Same thing with generic correlations. It was slightly biased for the 250 observations per environment. They became fully unbiased at the 3,000 individuals per environment mark. And likewise, the precision increased by, as you know, which is measured by the decrease in standard error. So the standard error of generic correlations went from 0.17 to 0.13. So limitations and other things to consider. For the simple implementation we made available and we described in this manuscript, we just use a method where the intercept is the only fixed effect, and that's when the methodology works at its fastest. That being said, having more and more random effects does not increase by a lot the computational cost of our method. It just means that we had to run an absorption of the fixed effects prior to run the model, so that it may increase by a few seconds, but that is regardless of the number of markers and observations. The correlated residuals. So one of the things that we got away and really increased the speed of our method was to avoid the cross-nectar product. But if the residuals were correlated, we will not be able to get rid of this cross-nectar product. And you might be thinking next for kernels and SVD. What happens if I have millions of markers? So one solution is to create a GBLUP and eigendecompose the genomic relationship matrix. And that can be done such that if you run a ridge regression of the principal components, you get the same result as running a GBLUP or a ridge regression. So that's an efficient way of bypassing the problem of having millions of markers to estimate. Another thing that's very interesting is that as the number of traits increase, and here we're talking 500 plus traits and traits that have very high correlation among themselves, it might be necessary to bend the covariance matrix here depicted by sigma beta. Bending simply means that we shrink a little bit off diagonals. And one thing that's nice to mention is that if you have up to 10 or 20 traits and your data is perfectly balanced, it is possible to get a RAMO to be efficient as well through a approach called canonical transformation or kernel diagonalization. So there are cases where RAMO can be efficient as long as your data is perfectly balanced and the number of traits is not too large. A general recommendation for multivariate models, as you are looking for estimate those covariance components and get that extra predictive ability, is that if you have very small data sets and you feel comfortable with RAMO, just go for it. RAMO is a little cumbersome to handle, but if your data set is small, you might as well just use RAMO. In that range of 5 to 20 traits for a small to moderate size data set, people you have been using in the past Gibbs sampling, which is more stable than RAMO, with very satisfying outcomes. However, if your number of traits is large or your data set is large, we would recommend you to move to the proposed approaches, PEGS, THGS, so pseudo-expectation Gauss-Seidel or tilde-hat Gauss-Seidel, which can really speed up the computation of large models. And myself, I'm very comfortable with running those models even if the number of traits is not too large. And last but not least, a model that is somewhat novel, just like the methods we are describing in this study, is a approach developed at the UC Davis by Dan Runcie called the Mega LMM, which is a model for highly correlated traits, and when the number of traits is larger than the number of observations and number of markers. So if you have thousands and thousands of traits in a relatively small to moderate size data set, you can run this Mega LMM which is it's a MCMC based method, but with a very efficient decomposition and works reasonably well for a very large number of traits. So the conclusion, just for the final remarks, is that multivariate models are very valuable. We need them to get those genetic correlations, that you can do a whole lot, classify traits, classify environments, and create selection indices. But in the past, they have been computationally unfeasible. The second remark is that now with this efficient estimation of coefficients through the randomized Gauss Seidel and efficient variance component estimation through pseudo expectation until the hat, we can run these very large multivariate ridge regression models. And last, we compared those methods. We showed that the tilde hat and pseudo expectation are very suitable replacements to REMO, especially for large data sets. And with that, I thank you all, and I hope I didn't bore you too much with the mathematics, but I hope you understand that this methodology is very valuable, and as we understand more and more the usage of multivariate methods, that can be a big enabling technology in plant breeding. Thank you very much.